Hello calculus folks, here we are again, and in this problem we're going to work on finding the acceptable x interval for which we can replace cosine with a second order Taylor polynomial. So what we're going to do is we're going to consider the function and does it equal the second order polynomial with and what will our remainder be for the second order polynomial. We want to make sure that the error does not exceed 0.01. So what we basically do is let's write out the Taylor polynomial. We have 1 minus x squared over 2 factorial, and what you have to notice with cosine is cosine does not have a third term. So typically R2 would be the third derivative at some arbitrary value c times x to the third over 3 factorial. But if we use that, then the third derivative would give us a misleading idea that our error is going to be 0 because our third derivative of this series is 0. So that forces us to go for our second term. We have to go to the next existent derivative. So that would be the fourth derivative, and use x to the fourth power all over 4 factorial. When we do this, so that's kind of a little bit of a movement away from, we saw the Rn. Rn before was the n plus 1 derivative at some arbitrary value times x to the n plus 1 all over n plus 1 factorial. But this has to be, remember, this is if that next derivative exists. So since it doesn't exist, or the value is 0, you have to go to the next derivative. So you want to use the next available polynomial term. So if you remember, cosine basically goes x squared over 2 factorial plus x to the fourth over 4 factorial. So what we're basically doing is we're heading out to the next term, which is the fourth. So let's calculate what the remainder would be. So they said, not the remainder, but they told us that they want to maximize the error. Let's find the interval that doesn't force us to exceed an error of 0.01. So we'll just set 0.01 equal to what the remainder would be, and we'll put in our fourth derivative at some arbitrary value c. We have x to the fourth power all over 4 factorial, and then what we do is we're going to, well, let's calculate what the fourth derivative of this function is. Well, we said the 0th is cosine, the first is going to be negative sine of x, and as you keep going on down, you find that the fourth derivative is going to be cosine again, and all of these derivatives they're all maxed out. Their max value is 1. So we're going to just plug a 1 in there for that derivative. And remember, this is specific to the function. If we had a different problem and it wasn't cosine or sine, but let's say it was e dx or square root of x, you would have to judge that derivative max value differently depending on what type of function you have. And that's what makes this type of work a little bit more challenging, is having that insight into what's going on. So I have everything set up. Now I want to solve for my interval. So I basically have x to the fourth over 4 factorial is 24 equals 0.01. So x to the fourth is equal to 0.24. Let me just double check that. I just don't want to make a mistake on video. 0.24. So now we take the fourth root of 0.24, and I get my interval to be x will equal 0.6999 radians. So let's go to the graphing software and see how this holds up. I'm going to just pause the video and get the grapher up and going, and then that will save your time. Okay, so here we are. We're going to graph cosine of x, and there's cosine. And then we're going to put in the Taylor expansion, 1 minus x to the second over 2 factorial. And hopefully you see that, wow, the fit for cosine matches pretty well with the cosine in a certain domain. So now we're going to just check our error. So I'm just going to write cosine of x minus our fit. So I'll just cut and paste that. So taking advantage of some of these free tools on the internet, and make sure you have your parentheses in. Oops. And there we go, we have the parentheses in. And now, so what you can see here is this blue graph represents the error, and you can see like within a certain domain our error is pretty good. I'll just look at these different points, and you can see here I'm just kind of clicking on the value. You can see here my error, if I just kind of crawl to the right a little bit more, I get to 0.01. My error curve says that I can go up to 0.7 and then get my desired error of 0.01, or I can go back the other way. If I go to negative 0.7, yeah, that's not going to, I get to the error of 0.01. But if you're not, if you don't find that to be helpful, we can just, I'll just cut and paste this function, and I'll make a table out of it, and then I can just type in the values that our calculation came up with. I'll put in 0.699, and I'll put in negative 0.699, and you can see that our error says that we're only at we're below what the specified error was. And I hope you find this kind of interesting, because you can actually see a picture of the error curve and the error table, showing us that our error theorem, estimation theorem, is working out pretty nicely. So I hope this video helps, and remember that whenever you're working with Taylor polynomials now, you can quickly get a quick visual of how your polynomial is actually fitting to your actual function by using this type of a tool. Please like or subscribe to this channel, and let me know if there's anything else you'd like to see. You can either send me an email or let me know in class. Take care, guys. Hope everything's going well.